In 2018, the team behind NASA's Mars rovers sent a robot called Orpheus into a place far stranger than space, into the darkness beneath 11,000 meters of ocean, where pressure crushes nearly everything humans have created. Why would the world's top space agency risk their best tech on Earth's most hostile frontier? The answer is not just science. It is about preparing for survival where no GPS can guide you, no signal cuts through the black, and a single flaw means instant failure. The ocean may be the only place tough enough to train robots for other worlds, and what NASA is learning here could decide if life ever makes it off Earth. So what does success really mean when the abyss itself becomes the proving ground? Orpheus enters the deep ocean alone, guided by a set of instructions written not by human pilots, but by software. In the darkness beneath thousands of meters of water, it cannot rely on real-time steering or outside help. There is no GPS signal at these depths, and radio waves vanish almost instantly. Instead, Orpheus depends on an internal sense of direction, an algorithmic memory built from cameras, sonar, and inertial sensors. Each dive begins with a map that is, at best, incomplete. As the vehicle moves, it constructs a three-dimensional model of the seafloor in real time, stitching together fragments from sonar pings and visual cues. This is not just data collection, it is a process of turning the unknown into something the robot can navigate, recognize, and return to. The Autonomy software at the heart of Orpheus draws on years of Mars rover experience, but the ocean's challenges are unique. The vehicle must detect obstacles, avoid cliffs, and adapt to sudden changes in terrain, all without waiting for instructions from the surface. Its navigation stack fuses information from multiple sources. The inertial measurement unit tracks every acceleration and turn, while stereo cameras and short-range sonar build up a picture of the immediate environment. When visibility drops, or when the landscape turns to featureless mud, the system falls back on dead reckoning, estimating position based on previous movement and sensor drift. Success is measured by more than just reaching a destination. Orpheus must be able to repeat its missions, returning to the same patch of seafloor and producing maps that match each time. This requirement for repeatability pushes the limits of onboard perception and decision-making. The resulting three-dimensional mapping products are not just scientific records, they are navigational tools, allowing the robot to make informed choices in real time. In the absence of human oversight, the software's ability to interpret its surroundings becomes the difference between a completed mission and a lost vehicle. Autonomy and mapping in this context are not abstract goals. They are the foundation that makes every deep dive possible. Every deep-sea mission begins with the expectation that the vehicle will not only reach its target, but return ready to go again. For NASA and its partners, a single successful dive is never enough. The real measure is whether the robot can repeat its performance, day after day, mission after mission, without catastrophic failure or time-consuming repairs. This standard of repeatability is not a luxury. It is an operational demand. The ocean does not forgive mistakes, and every hour lost to troubleshooting is an hour without data. Orpheus was engineered around this mindset. Its systems are designed to withstand the crushing pressure of the Hadal zone, up to 1,000 times atmospheric pressure at 11,000 meters, without needing a full overhaul between dives. The vehicle's aluminum frame is drilled with precision to reduce unnecessary weight, while its body is molded from syntactic foam, a material packed with microscopic glass spheres that resist collapse. Every seal, connector, and housing is rated for the maximum depth the ocean can offer. Even the payload bays are modular, allowing sensors to be swapped or upgraded with minimal downtime. The goal is to create a daily mission cycle: launch, map, sample, recover, recharge, and relaunch. This routine is a far cry from the one-off heroics of earlier deep-sea exploration, where a single descent might end a program. Instead, Orpheus is expected to operate like a workhorse, building a consistent record of the seafloor that scientists can trust. Each return to the same site is a test of both the robot's memory and its mechanical resilience. If the data matches and the hardware survives, the mission is working as intended. This focus on endurance and reliability is not just about efficiency. It is a rehearsal for the even harsher environments of other worlds, where recovery is impossible, and every system must be trusted to function under relentless, invisible pressure. At sea level, the weight of the atmosphere presses down with about 14.7 pounds per square inch. Descend just 10 meters underwater, and that pressure doubles. Keep going, and the numbers climb fast. By the time a vehicle reaches the bottom of the Mariana Trench, nearly 11,000 meters down, the pressure has multiplied to roughly 1,000 times what we experience at the surface. That is more than 16,000 pounds pressing on every square inch, from every direction, with no relief. There is no up or down in this kind of force. The crushing load is omnidirectional, squeezing hulls, connectors, and every seam equally. This is not a distant, abstract number. It is the difference between a system that functions and one that collapses in milliseconds. A single flaw, a microscopic crack in a pressure housing, or a tiny imperfection in a seal can become a fatal weakness. At these depths, water does not simply seep in, it blasts through with the violence of a shaped charge. That is why every component on a vehicle like Orpheus is rated for the full 11,000 meters of load, even if most dives never reach that extreme. The margin for error is measured in fractions of a millimeter. The challenge is not just surviving a single dive, but doing so repeatedly without cumulative damage. Pressure at this scale is relentless. It tests every decision made in design, every material choice, and every manufacturing process. In the deep ocean, the laws of physics are the only authority, and they do not negotiate. Every component on a deep-sea vehicle faces a silent, relentless adversary. At Hadal depths, the pressure is so great that even the smallest imperfection can spell disaster. A pressure housing might look flawless to the naked eye, but a defect measured in microns, a hairline crack, a manufacturing blemish, or a tiny air pocket can become the origin of total failure. The water outside does not wait for a weakness to grow. It forces its way in, seeking out the most vulnerable point and exploiting it in an instant. Seals, gaskets, and connectors are especially at risk. These are the interfaces where different materials meet, each expanding and contracting at slightly different rates as temperatures shift. Over repeated dives, the constant cycling between surface and abyss can cause fatigue, making these junctions even more susceptible to failure. A seal that works perfectly on the first dive may begin to deform or stiffen over time, creating a pathway for water to invade. The same holds for the syntactic foam and aluminum frame. Syntactic foam resists collapse by distributing pressure across millions of embedded glass spheres, but if just a few spheres are flawed, the damage can spread. Aluminum, chosen for its strength-to-weight ratio, can develop stress fractures at bolt holes or sharp corners, places where force concentrates. The margin for error is vanishingly small. Survivability demands that every design choice, every weld, every batch of material is scrutinized and tested. There is no backup plan if a flaw escapes notice. In the deep ocean, the environment is not passive. It is actively trying to find a way in, and it only has to succeed once. On May 10, 2014, Nereus slipped beneath the surface of the Kermadec Trench, aiming for a depth of nearly 10,000 meters. Telemetry streamed back to the support ship, each data point confirming the vehicle's steady descent. At 9,990 meters, where the pressure reaches about 16,000 pounds per square inch, Nereus continued its survey, relaying video and sensor readings from a world almost no machine had seen. Then, without warning, every signal vanished. The data feed cut to black. No acoustic pings followed. The ship's crew waited, scanning for any sign of recovery, but the silence was absolute. In the hours that followed, small pieces of plastic floated to the surface. These fragments were all that remained. Investigators pieced together the story from the debris and the abrupt loss of contact, a catastrophic implosion triggered by a single, undetected weakness in the pressure hull or a connector. At this depth, water is not gentle. It is a force that smashes through metal and composite alike, pulverizing everything inside in milliseconds. The shockwave leaves little behind. No large sections were ever found, only scattered shards that told of the violence below. Nereus had been engineered for the Hadal Zone, its systems tested for the rigors of deep-sea exploration. Yet even with years of design and successful missions, the vehicle was erased in an instant. The loss was not just a technical failure, it was a reminder that the deep ocean offers no forgiveness. Every dive is a confrontation with forces that can overwhelm even the most advanced machines. In the wake of Nereus's destruction, the engineering community did not retreat from the challenge of the Hadal Zone. Instead, the loss became a catalyst for a new generation of design philosophy, one that treats every mission as a test of survival, not just of performance. Engineers at Woods Hole and the NASA Jet Propulsion Laboratory began to scrutinize every step of the process, from material selection to assembly and pre-dive checks. Redundancy became a core principle. Critical systems could no longer depend on a single seal, connector, or housing. Where Nereus relied on proven but centralized pressure hulls, the next wave of vehicles, including Orpheus, adopted modularity, spreading risk across distributed systems and making it possible to swap out components without dismantling the entire vehicle. Pressure testing protocols grew stricter. New vehicles faced hydrostatic testing to depths well beyond their operational targets, often up to 1.5 or 2 times the intended maximum. Each batch of syntactic foam, every welded joint, and all electrical connectors underwent close examination for micro defects. Failures in the lab, once seen as setbacks, were now considered essential data points in refining the design. No longer was it enough for a system to survive a single descent. Survivability meant enduring repeated cycles of crushing and release, withstanding fatigue that accumulates over dozens of dives. The shift did not stop at hardware. Mission planning began to emphasize the value of fleets over single vehicles. The goal was not a lone pioneer, but a persistent presence, multiple robots working together, each able to pick up where another left off. This approach, inspired by the modularity of CubeSats in space, promised not just resilience, but scalability. If one robot failed, the mission could continue. The lesson from Nereus was clear. In the deep ocean, reliability is built on layers of backup, rigorous testing, and the humility to expect the unexpected. In March 2012, James Cameron descended alone to the bottom of Challenger Deep, reaching a depth of 10,908 meters in the deep-sea Challenger submersible. The vehicle itself weighed about 11 tons, yet every kilogram counted. To survive the descent, Cameron's team engineered a pressure sphere just over 1 meter wide, forged from thick steel and shaped to distribute force equally in every direction. The sub carried over 1,000 kilograms of syntactic foam, a material packed with hollow glass microspheres designed to resist collapse under pressure. Ballast weights provided the downward force needed to reach the seafloor, and a carefully calculated release system allowed for ascent. Inside the cramped sphere, Cameron relied on a life support system that could scrub carbon dioxide and provide oxygen for up to 56 hours, a margin chosen to outlast any plausible rescue window. Don't forget to subscribe. Every design choice came with trade-offs. More batteries meant longer mission time, but added weight force reductions elsewhere. The need for thick hull walls left little room for comfort or scientific payloads. Even the shape of the sub was dictated by physics, a narrow vertical profile to minimize the stress of descent and return. Cameron's dive was a singular achievement, but it also highlighted the limits of human presence in the Hadal Zone. Each mission required months of preparation, a support ship, and a team of engineers on standby. The risks were personal and immediate. For NASA and ocean engineers, these constraints set a benchmark. If a robot could match the reliability and survivability of a crewed sub, but operate repeatedly and autonomously, the door to routine exploration would finally open. Cameron's journey stands as both a technical marvel and a reminder of what persistence demands when the stakes are measured in lives as well as machines. With no access to GPS, Orpheus must invent its own sense of place in the dark. Deep below the surface, the vehicle's position is calculated from raw acceleration and rotation data gathered by its inertial measurement unit. Every surge and turn is recorded, but over time, tiny errors add up. To correct this drift, Orpheus relies on a network of overlapping sensors. Short-range sonar scans the seafloor, measuring distance and detecting sudden drops or rises. Stereo cameras capture overlapping images, searching for patterns and features that can be matched from frame to frame. When the terrain is rich, ridges, rocks, or scattered debris, the system locks on, updating its internal map. In stretches of flat, featureless mud, the robot must trust its last known heading and speed, using dead reckoning until the landscape changes. The algorithms running on Orpheus fuse all this information in real time, weighing the confidence of each sensor and recalibrating as new data arrives. This process, known as terrain relative navigation, allows the vehicle to make local decisions, veering around an unexpected boulder, hovering to inspect a patch of unusual sediment, or retracing its path to a known waypoint. The Autonomy stack is designed to function in total isolation, with no outside correction, making every meter of progress a test of self-reliance. This approach is not just a workaround for the ocean's blackout, it is a blueprint for how machines might one day steer through the hidden oceans of other worlds, where help from above is never coming. Radio waves, the backbone of surface communication, are useless in seawater. Instead, Orpheus relies on acoustic signals, sound waves that travel slowly and have limited bandwidth. A single message can take seconds to arrive, and only the most essential data can be sent in real time. Every bit of information comes at a cost. Tethers such as fiber optic cables offer high-speed links and steady power, but they carry their own risks. A tether can snag on seafloor ridges or become tangled in debris, forcing engineers to choose between safety and freedom to roam. Untethered, Orpheus gains range and maneuverability, but it must operate with the knowledge that if something fails, there is no way to intervene until the mission ends. Power is just as unforgiving. In the perpetual night of the Hadal zone, artificial lighting is not optional, it is the only way to see. High-intensity LEDs cut through the darkness but drain batteries quickly. Thrusters, needed for precise movements, and station keeping near the sea floor are another major draw. Every maneuver, every minute of illumination, chips away at the vehicle's endurance. Engineers balance these competing needs by rationing power, using low-draw cameras when possible, and planning routes that minimize sharp turns or extended hovering. The result is a constant negotiation between ambition and survival. Each mission is a test of how far a robot can go, how much it can see, and how long it can last before the limits of communication and energy force it to return. Every dive beneath Earth's trenches pushes the limits of what machines and humans can survive. As NASA engineers build for Europa's ocean, they also reveal how much of our own planet remains uncharted and unforgiving. The next leap in exploring other worlds will depend on what we learn from the darkness below us right now. The frontier isn't distant, it's waiting beneath our feet. Share your thoughts below.